Yes, thank you. Thank you for the introduction, and also thanks to Digital Future for organizing this very useful and very insightful series of seminars. As the title suggests, today we will talk about how artificial intelligence, and we will define what we mean artificial intelligence in a second, means or may mean for sustainable development. And this also enters in a series of studies that try to look at how we can use the 17 goals of the Sustainable Development Goals, and more specifically, the 169 targets that are within them, to understand, guide, and really coordinate policy projects across different topics. And in this case, we have tried to use this so-called Sustainable Development Goals, SDG lens, to try to analyze how the latest developments and potential future developments in AI and digitalization might affect the achievement of each one of the 169 targets of the SDGs. So this we will do in the first part, let's say, and we'll draw from this paper, which was co-led by Ricardo and I, and published in Nature Communications. But then we will also go in some more detailed examples regarding AI for fighting climate change, but also for fighting local air pollution. So any one of you that would like to know more, this is the key reference of the first part of today. It is a very multidisciplinary study, as I will show you in a few seconds. And also it was really nice to see how it got very, a lot of widespread attention, both in academia with many citations, but also in news articles and so on. So it has been quite a, let's say, famous article in the field, which started a lot of debate. And the motivation behind that study was to answer a simple question. So if there was evidence or published studies of artificial intelligence acting as an enabler, so having a positive influence, or an inhibitor, so negative influence, for each of the 169 targets. And as you can imagine, if you're familiar with the SDGs, they go across a lot of topics. They go across the environment, the society, economics, and really the kind of socio-technical systems that are behind all these goals. So to try to do a study like that, you really need a very multidisciplinary and comprehensive team. So, well, having learned from our previous efforts in this field, we assembled an authoring team able to assess both the breadth and the depth of knowledge on the potential implication of AI on sustainable development. And basically mapping topic to expertise and reaching out also to our extended network. So you see here authors both from KTH, but also from other university and teams. We could assemble this team with a wide-ranging expertise, ranging from the technical application of AI and machine learning to the understanding of the social sciences behind AI's societal impacts. And so, yeah, we have people from both natural and social sciences. And as examples, we cover AI fundamentals, interaction design, applied AI, and of course, also sustainability, energy, climate, and biodiversity. And the first step in this study was actually to define AI. We're very aware that AI is a term that is very used. And of course, to enter in a scientific publication, we really needed to have our boundaries clear. So what does AI mean, and what that definition means for its impact on the SDGs? So for this study, AI means software technology with either capacity of perception, an example are face recognition software, decision-making, so software that help medical diagnosis, for instance, prediction, like some of the software that is being used in weather forecast, automatic knowledge extraction and pattern recognition from data, interactive communication, like social bots that are a bit everywhere nowadays, and more broadly, logical reasoning, And this is quite a broad definition, which also includes machine learning. And the methods for such evaluation, so if you will download the paper that we're presenting today, you see there is quite a large supplementary material. I think it's like 40-something pages. And basically, in this supplementary material, you will see for each one of the Sustainable Development Goals. So for instance, here you see Goal 1, and poverty in all its form everywhere. And for each of the sub-targets, so here you see 1.1, 1.2, 1.3. So here we go for 169 lines. We try to answer this question. So how can AI affect positively or negatively the achievement of that specific target? So in a very simplified way, we did, let's say, 169 micro-literature search, which were, of course, expert-driven, and then discussed in the group to try to understand not only what this means across one dimension, but even more interestingly, what does it mean across all these dimensions as defined by the Sustainable Development Goals? As you will see, this is quite common. Our results are then divided into society, economy, and environment. So jumping to the result, and today we don't have that much time, so we'll just provide a few highlights, but then please ask us questions if you want to know more insights, and I would invite you, of course, to read our paper. This is a broad, let's say, summary of the result. Across the 169 targets that we evaluated, we found that AI has a potential positive impact on almost 80% of the targets, and a potential negative impact on around 35% of the targets. And this might seem, and this varies across economy, environment, and society. It might seem like a very good result for the development of AI, but also there are a lot of asterisks, let's say, to it. Because also we assessed in this figure, and I'll not go too much in detail, we assessed the quality of the literature, the quality of the evidence that we found in this study. And of course, we found that there are quite large literature gaps, especially when looking at the negative impacts of artificial intelligence. As you can imagine, it's easier to, as a researcher, to document and publish positive impacts than negative impacts. So, of course, this is quite a broad picture, but still, it gave us the possibility to have a snapshot of all these possible implications. And I think it gave us also a good entry point to understand what could be done for the future sustainability of AI. So maybe the easiest thing is to actually go into examples. And in this representation, you see all the Sustainable Development Goals with their logos divided across society, economy, and environment. To the right of each one of the Sustainable Development Goals, you see a number of boxes on top and on the bottom for each SDG. And the ones, and each one of these represent a target. So you can see SDG 1 as targets 1, 2, 3, 4, 5, A, and B. And then we highlighted it in green, where we found published evidence that AI, as defined previously, might act as an enabler for achieving that target. And below, in orange, we found evidence that AI might act as an inhibitor. Then, of course, it depends on the context, and it depends on different applications. But again, this is a global review that, of course, now we are working also to try to get to a more nuanced level for local applications. So some examples. AI can affect the poverty, economy, and industry. So AI-enabled technology might help new jobs and productivity, most times by increasing the efficiency of processes. And there are some interesting applications of AI, for instance, to fight poverty. So satellite data is being used to track areas of poverty, to then, without spending a lot of money, to go really in the field across the country, target activities to fight poverty. At the same time, AI, and it's defined in the article as a double-edged sword, also might increase inequalities depending on how it develops in the next few years. As in any transition, certain jobs will be lost. So jobs that are easily jobs that repeat themselves, or like with repeating tasks and so on, might be lost. And also there will be uneven opportunities. And this might result in increased inequalities. So of course, if you are in a society like in Sweden, which has very technological society with high penetration of computer, internet, and so on, you will have better chances to use this transformation and have more opportunities than in a low-income countries where the opportunities to access technology are not the same. And of course, you also see more and more in the news and well, in everyday life, how algorithms in certain websites and so on actually polarize society and increase discrimination by clustering, for instance, group of people in social media, depending on what they think. And of course, then polarized and unequal society can have impacts on peace and stability. More examples, and Ricardo will go more in depth into these. AI could actually potentially enable smart and low carbon societies. So if we talk about the energy transition, where we need more and more renewables, AI or smart algorithms can help integrating renewables in the electricity mix. But also it can help smart demand response in energy systems so that we have a more efficient system and more matched between demand and supply. And of course, supporting the creation of smart and low pollution cities can also have a very good health implications. As you're very aware, there are a lot of health implications and deaths due to air pollution, and AI can also help fighting that. And also, of course, some AI application can support the management of natural resources and resource efficiency. And maybe just doing an extra zoom on one topic of the many that are covered in this paper is looking at AI and climate action and the Paris Agreement. So I think many of you saw in the news the recent developments at the COP26 in Glasgow, with the headline that even though we have some progress, we're still behind in what is needed to stay into a 1.5-degree target. Actually, some applications of AI can help speeding this up. And this is just a couple of examples. AI is being used to try to understand better climate change. So here we're talking about climate adaptation. So how do we adapt to an increasing and advancing climate change? AI can support the prediction and forecasting of extreme weather events due to climate change. It can support predicting crops due to weather patterns. And all of these can benefit adaptation planning. And of course, then, as I said before, it can help mitigating, so reducing emissions, supporting low carbon energy efficiency, low carbon energy systems with high integration of renewable energy and energy efficiency. But again, with drawbacks. So using software technology, especially machine learning, it's very energy intensive. So a lot of electricity is needed for data centers, for these machines to run. And an example that is quite typical is, for instance, there might also be new needs that we didn't even envision before. For instance, cryptocurrency. And you might have heard that cryptocurrency applications such as Bitcoins are globally using as much electricity as some nations' electrical demand. And this is the kind of example where you have the impact, on the other hand, of that increasing software use might have. And just very briefly, I'll not stay here on this a lot. You might be aware that KTH recently also launched a climate action center, and we're also looking at how to make this collaborate with digital futures to try to address these two things together. So try how we can use the digital technology to address climate change, and of course, then other environmental issues with it. So closing our study, we also try to look at what are the different players that are in place when doing regulation and understanding what's happening with AI and more broadly technology in the world. And as you might know, well, as you have noticed, a wide range of new technologies are being developed very fast, significantly affecting the way individuals live. And of course, vice versa, technology tends to satisfy any new need of individuals. At the same time, fast technology development affects governments through need of appropriate piloting and testing, and governments provide legislations and standards to technology. The problem is that neither individuals nor governments seems to be able to follow the pace of these technological developments. So the government affects individuals through policy and legislation. And sorry, I forgot quite, even though it's written there, a thicker arrow here indicates a faster change. And at the same time, individuals require new legislation, which is consistent with the changing circumstances from the government. And of course, in all this picture, we have the environment that interacts with technology by providing the resources needed for technological development, and also is affected by the environmental impacts of technology. And of course, we are also playing all within the planetary boundaries. So as next steps from this study, we're really trying to understand and working also with people working, for instance, in AI ethics and so on, what is needed in this difficult social technological picture to try to direct AI so that it enables as many sustainable development goals as possible rather than inhibiting them. And this is, sorry, this was on the environmental impacts. And again, with this broad review that we did in this study, we also try to understand what we need to work more on. So now we know, what science knows, what can we do better? And of course, one thing that I already commented on is that AI is mostly developed in technology advanced nations. And we need to balance this so that the AI is beneficial across and within nations, so that it doesn't increase inequalities. We need to invest in AI safety as more and more of our systems, like our energy, our water, and so on, are regulated by, are managed by software, which can be vulnerable to cyber attacks. As I said at the beginning, we notice a bias into publishing positive results. So we need more work investigating potential negative effects of AI. And also a very important theme at the moment, we need more research into understanding what is ethical AI. And we need that research then to inform ethics-driven legislation and certification mechanism systems. So just a quick summary of this first part of the study, and then I'll leave it to Ricardo to go more in depth into some applications, is that, well, AI, as you have noticed, is already affecting everyone's life, both in positive ways. We mentioned smart grids in cities, in e-health, but also somehow negatively. And you see some also social impacts that can be exacerbated by AI. And that is also only expected to increase. And this is a double-edged sword, as we said before. This could potentially enable an AI-fueled sustainable development. But as we have this mismatch between the speed of development of technology and what people and governments can manage, there's quite a lot of work to do to try to have, let's say, a sustainable AI development. And among all, substantial work is needed for overcoming gaps in transparency, safety, and ethical standards for AI. So I leave it to Ricardo now, my colleague, to go a bit more in depth into a more nuanced example of what actual AI and machine learning can do for a specific example.
Thank you, Francesco. Should I share the screen? Yeah, I will do that myself. And thank you very much for the invitation and for being part of this fantastic seminar series. It's also a pleasure for us. Now that you saw from Francesco the main areas where AI can help, and if you remember, he mentioned the example of SDG 11 on sustainable cities. It turns out that all the targets of SDG 11 can be positively affected by AI, and in particular, if we focus on air pollution, this is a very important area because 800,000 people die in Europe every year just due to the air pollution. So this part is going to be a bit more technical. We're going to show one example on how AI can actually be used for tackling some of the targets related to the air pollution in cities. And what we want to develop, as you can see in the slide, is non-intrusive sensing in urban flows. I'm showing on the left a very detailed flow simulation. So this is one obstacle, which represents one building. This is something called direct numerical simulation. So we are really solving in a lot of detail the flow around this obstacle. We have more complicated urban environments as well. And what we want to do is to take few sparse measurements, which are these black dots that you see here, and by using neural networks, reconstruct from those sparse measurements at the ground, the three-dimensional velocity field, together with fields of temperature and also sorry, Tigran, can you out it in full screen? This is in full screen, no? Yeah, I was in full screen mode, but I had shared the other screen. Okay, perfect. So now you can see it in full size, which is always better. So the idea is to use neural networks to go from the sparse measurements to three-dimensional representations of the velocity and then temperature, and why not the pollution concentration in these urban areas. How are we going to do that? Well, let's show some schematic representations. Here on the right, I'm showing very detailed simulations of various obstacle configurations. Here you can see two different obstacles where I'm increasing their separation, which leads to different flow regimes, as you can see here. I'm not going to go into the details of the simulations, just to know that we have very detailed flow data to train neural networks. And on the left, what I'm showing are different flow charts and different procedures by using recurrent neural networks or convolutional neural networks, so that we can go always from the sparse measurements on the ground to three-dimensional representations of the field at different distances from the wall. So we can have a more complete information and essentially enhance the initial measurements that we had from our just simple distribution of sensors that we have over here. What we can do, we can illustrate some of these examples by looking at areas that have to do with interpretability. This is a very, let's say, relevant area in the context of deep learning. Most of the deep learning models that we're using nowadays are not interpretable in the sense that we are treating them as black boxes. We know what is the input, we know what is the output, but we don't know what is the actual relationship between those inputs and outputs. And there are other machine learning approaches which are interpretable, but typically they don't have the same accuracy as deep neural networks. What we do here is to propose a number of strategies to add layers of interpretability to these deep neural networks. This is a study, well, a summary of methods that we just published in Nature Machine Intelligence. You can see the reference over here. So this is 2021. And essentially, for example, the method by Kramer and others, which involves inductive biases, is also quite promising. So here, the example that I show is connected to what Francesco mentioned before, SDG 1 on no poverty, how one can use satellite images and convolutional networks to track those regions of poverty. If it turns out that we have interpretability, if we can connect the inputs, which can be the features obtained in the images, and the output, which is the production, basically the consumption per capita, then not only we can predict the regions of poverty, but we can understand the dynamics, and we can see temporally if a certain area is at risk of being in this situation, and we can coordinate better international actions to tackle that. So interpretability as an additional layer to tackle the SDGs is a very, very important area. This has to do, of course, with the urban example. If we are able to predict the pollution levels and we don't know the interpretability of our model, we are also having a quite limited picture. So our eventual goal is to have models that can take us from those dispersed measurements to the three-dimensional representations of the flow and the pollutants with the layer of interpretability. So we know what are actually the inputs that are more important towards obtaining accurate outputs, essentially. So if we go now more to the technicalities, these are some examples, and now I will talk a bit more about fluid mechanics and machine learning applied to fluid mechanics. Essentially, there have been many approaches to do this, to predict the flow based on the input, which is below. I'm using the wall information to predict the flow above the wall. And many of these approaches are linear. They're linear methods which connect the input and the output. But as you can imagine, by looking at the pictures that I showed before, the flow in urban environments is very complicated. It's turbulent. And turbulent flows have interactions that are not only linear. There are also very important modulation effects, which are mostly non-linear. Therefore, in this article a couple of years ago in JFM, we showed that it's important to use nonlinear methods to make this type of predictions. And of course, neural networks, and in particular, deep neural networks, give us the possibility of creating such nonlinear models. And therefore, there is quite some potential to exploit these methods to conduct this type of predictions. What we wanted to do was to illustrate the usage of deep learning to make these predictions in a geometry that is a bit simpler than the obstacle on the city. By the way, what I'm showing today for this simpler geometry, we are already doing it for the urban environment, but it's a bit easier to explain in this simpler example. This is basically an open channel. You have a wall and you have the flow above the wall. And like in the example of the city, I will use the input at the wall to predict what happens at different distances away from the wall. These are some details about the numerical data that we will use as training data set. You can find all the details in this reference, was Tony and others in the Journal of Physics conference series, and we will create on the order of tens of thousands of snapshots to be able to train the deep learning models that we're going to use. Let's keep in mind, to give a little bit of perspective, because maybe the audience is a bit diverse and perhaps not everybody has the same background in deep learning. One can use fully connected layers to perform predictions using deep learning. The problem of this type of network is that the spatial information in the input is lost, because as you can see in this input layer, all the points.
Thank you, my volume control.
Sorry, there is some sound. Yeah, I think now it's better. So if you use a fully connected network, you are missing the spatial information in the data. However, there is another type of network, which is very popular in computer vision, which is the convolutional neural network. And as you can see, the way that this model works, you have your input here. You have a little kernel, which is a little window, which is sweeping through the input, and it applies a convolution operation to obtain a feature map. So the result of this convolution operation are features that are being highlighted, that are being obtained from the input data. So the advantage of these convolutional networks is that the amount of parameters that you have in the first layers is significantly lower than that required by the fully connected networks, because you only have this little window that is sweeping through the image, instead of having all the grid points connected to the next layer. Let me talk a bit about the architecture that we actually considered in this work. I remind you that I'm using the information in the blue plane, so that's the wall, to predict what happens on the yellow plane, so on a plane above that wall. In this case, we're using two physical variables that have to do with the shear, so the friction of the flow on the wall, and I'm going to predict the velocity away from the wall. So I'm going to connect the input with the velocity away from the wall. Okay, and this is going to be done via convolutional neural networks, because these networks are very good at exploiting the spatial features in the data. Now, when I show you some results, you will see that the characteristics of the flow, they have very distinct features that one can exploit to make this type of predictions. This is the architecture. In the first model that we use, we have two inputs, so two channels in the input layer. We have a total of 6 hidden layers, and then our output has one channel, which is the velocity above the wall. So remember, I use the sensors on the plane on the bottom to predict what happens above. And this is a bit more information. We use the ReLU activation function. We have 128 square grid points, so this is a quite densely populated input plane that we have here. And the filters that we use in the first layer have a depth of 2, because of course I have 2 inputs. The kernel has a size of 5 by 5, And here, actually, you cannot see these numbers in this format of the slides. But here, what I'm also indicating is the number of feature maps that are being obtained after each convolution layer that I'm applying. So in the first layer, I have 64 feature maps. So this type of filter is applied a total of 64 times, which is still less than what it would cost to have a fully connected network for this same problem. Without going too much into the details of the convolutional network, the idea is that as I go deeper into the network, the receptive field, so the points used from the input to make the prediction, gets larger. So I can build hierarchically the information in a way such that the first layers are identifying more concrete features, and the deeper layers are building hierarchically more and more complicated features. So I can go from smaller things identified in the flow to more and more difficult features, more and more difficult structures that are going to be relevant for the output that I end up having at the end. Okay, so this is the hierarchical characteristic of the convolutional network, which is of course very well suited to predict the hierarchical characteristics of these flows that exist in the urban environments because they are turbulent. So this is essentially what I'm mentioning, that as I go deeper, I get larger and larger features. And at the end, you could have basically two types of networks to close the model at the end. You could have a fully connected network in the last layer, and that would give me a global output. A fully connected layer at the end would be used to have a classification problem. I give you this image, I apply all the convolutions, and the output is a car. It's just a label. And the output is not another image, it's just one label, so I have a global output. What we're going to be doing is a different approach, because we want to have as an output another image. We don't want to have a label, classification label, we want to have an image. So we're going to be used what is called a fully convolutional neural network, which means that all the layers are convolutional. In this case, you can see the example of these cars. This will give me a local output where this network is identifying if in this street I have a car, a building, a pedestrian cross. That local output is achieved through having convolutional layers all the way to the end. Okay, and that's the approach that we're going to adopt in our problem, because our output is going to be a plane with physical information in all the grid points that I have initially in my input. Okay, so this gives you an idea of what I find in my results. Again, I will not go too deep into the fluid mechanics. I will stick more to the AI, to the deep learning part. This is the predicted flow at a distance of 15 plus units, which means that it's quite close to the input. So the input and the output are quite close to each other. The second row is the reference. And this is how the flow looks like. And you can see the important message for the audience here is that this has a very distinct pattern. It has elongated structures. And these structures that exist within the chaos of the urban flow are what the neural network is picking up to make the predictions. The network is building hierarchically these structures to be able to exploit the information and make relevant predictions. The first row is a linear method, the one that I was mentioning at the beginning, that is not so accurate for complex nonlinear flows. And the third row is the nonlinear neural network prediction, which, as you can see, gives a much better result, not only in terms of the intensity of the fluctuations, but also in terms of the modulation characteristics, how complicated are the patterns of these little streaky structures that you can see here. So the neural network is much better because it captures more of the physics that is present in the flow. As I go farther away from the wall, so now my output is a bit farther away, the linear method starts to really saturate, so it doesn't really show so much. The neural network still reflects quite well the spatial features of the output data. When I go very far away, the linear method basically doesn't show so much because the correlation between the input and the output is just very small, but the neural network, even if it exhibits worse predictions, a deterioration of the predictions, which is natural because the data is less correlated, the spatial features in the data are still reproduced. And I will show you more about this in a second. To give you an idea of the statistical performance of the model, with this approach, we can predict the fluctuations with less than 3% error, whereas classical methods are between 15 and 40% error. So we can actually overpredict significantly the classical methods. And I will show you a refinement of this approach that gives us even better results. The refinement comes here. Now I'm going to consider, first of all, a higher Reynolds number for the people who are not into fluid mechanics, essentially a more turbulent condition, a more challenging case. And I'm going to consider 3 inputs. So I'm going to measure at the wall more information, and I'm going to predict more information as well. I'm going to predict the velocities of the flow in 3 different directions, in the streamwise, wall normal, and spanwise directions. So essentially, I use more input information, but I also predict more things. The key of this architecture is that I'm going to, well, I will tell you more in a second, but I emphasize aspects such as the periodic padding, which have to do with the typology of the data that I use as an input for this convolutional network. And what I showed you so far is an approach that we call FCN, fully convolutional network. I also introduced another approach, which is the FCN POD. It's a fully convolutional network together with a proper orthogonal decomposition. The only thing that we are doing with this method is to decompose the spatiotemporal information. The velocities depend on space and time. I decompose that information into spatial modes and temporal coefficients. So I separate the contributions, and my FCN POD network is only predicting the temporal part. It doesn't care about the spatial one. The result is the following. Here I'm showing again the velocity fluctuations. The first column is very close to the wall. The second column is very far away from the wall. The reference is the third row, which you can see is more chaotic, more turbulent than when I was showing before. The first row is the linear method, which again doesn't really predict so well the results. And perhaps the most interesting result of this part is that the FCN approach works very well when input and output are very close to each other. Then using a fully convolutional network is the way to go. When the input and the output get farther away, and therefore the data is less correlated, then you should go towards the FCN POD, because the POD, this modal decomposition, encapsulates very well in those modes the spatial information of the larger, more energetic scales, and predicting only the temporal information is more efficient than aiming at predicting the whole plane and the whole fluctuations on that location. This can also be seen statistically. Just to give you an idea, here we obtain less than 1% error when the input and the output are very close. When we move farther away, the FCN POD gives us quite good predictions on the order of 20% error, which is less than half the error of traditional methods, which gives us some confidence in the methodology that we are developing here based on convolutional networks. Okay. This is about transfer learning. Perhaps I will not go too much into this because we don't have so much time, but just to hint, I actually like very much the results of transfer learning. The idea of transfer learning is that you can use a network trained for one task, and you can transfer those weights to perform a different task. What we show here is that by doing transfer learning, you can save your training data by a factor of 4. Because essentially you don't need to rerun cases, that are a bit different, that are more chaotic or more turbulent. What you need to do is reuse the information that has been trained already based on other databases, and then the amount of training data required for a new task is much, much lower. And this actually very nicely shown in this reference, Guastoni and others in the Journal of Fluid Mechanics. So if you are interested in this, please have a look at this publication. And perhaps the last thing that I will mention in this more technical part is what happens when my input, the thing at the wall, is actually very coarsely measured. Because what I have told you so far has been relying on using the whole wall information as an input. But the picture that I showed to motivate this section on the R-band data was just a bunch of black dots. It was just a bunch of sparse measurements. So what happens when I don't have densely populated input data and I have very coarsely measured inputs at the wall? Well, it turns out there are different ways of doing this. We use the GAN methodology, generative adversarial networks. For the ones who are not familiar with these networks, you have a schematic representation here. So I have two parts of this network. I have a generator, which has the task of producing high resolution images from low resolution ones. And I have a second part of the network, which has the task of identifying which of these images are real and which ones have been produced, manufactured by the generator. And these two parts of the network are trained together using game theory, which in the end leads to very, very accurate predictions. So both of them become very good at their own jobs. And what you can see here on the bottom, I will just highlight some of the results. Here is the reference wall information with full resolution. Here on the top, I'm considering different levels of downsampling. So I'm making that input coarser and coarser. And what you can see on the second row is that the results are always very physical. So I'm getting the right location of the structures, I'm getting the right separation of the structures, and the more downsampling that I apply, the more attenuation in the fluctuations. But the important thing for these predictions is rather having adequately located streaks, adequately spaced structures in our flow, and that's obtained pretty much accurately with the GAN methodology that I show here, which, by the way, is also, all the results are also published in another article by Güemes and others in the Physics of Fluids journal from this year. And just to be on time, these are some future applications that we're looking at, but perhaps what I want to also show is a concluding slide from the two parts. I mean, we talked about the SDGs. We saw the positive potential of AI on 79% of the targets and the importance of having a global debate to be aware of the limitations and the needs in terms of regulations. Everybody is going to be affected by AI, so everybody should be part of this dialogue. In particular, experts in AI should be part of the process to develop regulatory actions. It should not be a political action. It should be involve not only practitioners, but also researchers in AI. This is a very important transformation that we're living, and we believe that it should involve all the relevant actors to make the best of these regulations. And I showed you one example of SDG 11, related to SDG 11. How can one predict accurately flow quantities, pollution levels in turbulent flows to be applied in urban environments with, in some cases, less than 1% error, which we believe can be quite instrumental to develop adequate regulations in the context of urban sustainability. And with that, I would like to, well, I leave here my information and, you know, my social media as well. So if you want to discuss more, I'm available to discuss. And now Francesco and I are happy to answer all your questions. Thank you for listening.